Let us take some more examples on vector space. The first example, we have already discussed this example. So that the set of real numbers R itself is a vector space with respect to usual addition and scalar multiplication of real numbers. So how to check it? That first we have to check that it satisfies the following 10 properties. So first property, closure axiom, satisfied. Why? Because addition of two real number is real number. Associative law also satisfied. 3, additive identity also satisfied because 0 is the additive identity. The fourth property, additive inverse. So if x belongs to R, then minus x is the additive inverse of R. So it is also satisfied. Commutative law always satisfied. Closure axiom with respect to scalar multiplication. So we know that multiplication of two real number is real number. So it also satisfied. Distributive law of scalar over vector also satisfied. Distributive law of vectors over scalar also satisfied. Similarly, associative law is satisfies, and the last 1 into real number is always a real number. So unitary law is also satisfied. Since all the properties of being vector space are satisfied by the set of real numbers, hence the set of real number R itself is a vector space. Let us take one more example. So that the set V of all pairs of real numbers of the form 1x with the operation defined as 1x plus 1y, which is equal to 1x plus y, and k times of 1y is equal to 1 into ky is a vector space. So let us take all 10 properties. Closure axiom, yes, it's satisfied. Associative law satisfied. Additive identity satisfied because 1 and 0, like that. 1, 0 plus 1x, which is equal to 1 plus 1 into x plus y, which is equal to 1, 0 plus x, which is equal to 1x. So 1, 0 is the additive identity. Similarly, additive inverse also satisfied. Here 1 minus x is the inverse of 1x. Let us add this 1x plus 1 minus x, which is equal to 1x plus minus x, which is equal to 1, 0, and 1, 0 is nothing but the identity element. 1 minus x is additive inverse of 1x. Commutative law satisfied. Closure axiom with respect to scalar multiplication also satisfied. Distributive law of scalar over vector satisfied. Distributive law of vectors over scalars also satisfied. Associative law and unitary law are also satisfied. Hence, V is a vector space. Let us take the next example. Let V is equal to matrix of order 2 by 2 and all elements are real number M 2 by 2 of R. The set of all 2 by 2 matrices with real entries for any A is equal to A, B, C, D, D equal to P, Q, R, S. In V, A plus B is just simple matrix addition, and K into A is equal to K times of A, K times of B, K times of C, and K times of D, so that V is a vector space. So we have to prove again the 10 property, closure axiom. We know that addition of two matrix is again a matrix, satisfied. Associative law satisfied. 0, 0 is the additive identity. And minus A, minus B, minus C, minus D is the additive inverse of A, B, C, D. Commutative law satisfied. Closure axiom with respect to scalar multiplication also satisfied. Distributive law over scalar as well as vectors also satisfied. Associative law also satisfied, and unitary law is also satisfied. Since all the properties of being vector space are satisfied by the given non-empty set V, therefore V is a vector space. Thank you.